of Things R&D for technology labs at Accenture. We tend to do the first of its kind deployments and figure out the technologies involved in a new space. And as we all know, and we're here, Internet of Things, and especially as it applies to industry and large business, is a new area for the industry. So for this talk, I'm going to walk through a journey. So I'm going to talk about a story that is probably similar to a lot of where others are going through about getting started. So the way that it's structured is that I'll start with an architecture and the principles around the initial applications and the architecture that you need to support that. And then as that architecture scales, both in terms of the volume of data, but more importantly in terms of the use cases, the applications, the data sources, the data types, that's a different type of scale, right? So we talked about contextualization, excuse me. So as we make these trade-offs to scale to accommodate new domains, new use cases beyond that initial set of applications, there's some new trade-offs that come to play, that come to bear, and then how do you handle that? And then finally, I'll conclude with lessons learned. So based off these trade-offs that we're seeing today, how do you accommodate for that? And then another way to look at this talk might be a different way. So for the initial applications, those architectural principles, I would say those are fully baked. Those are things that we have in production, we know how to do. The trade-offs are the things that we're seeing today as those initial applications scale to new use cases, new analytics, new data sources. So for things in that space, I'll call that half-baked. So I want to talk about some ideas and some concepts that we're looking at. And then finally, for our lessons learned, I guess those would be things like hypotheses and ingredients. So ways that we think about dealing with these problems and that we think can address interoperability. So the focus of this talk is really around the platform. So in the use cases of industrial internet, you have your physical world, the things that you want to know about. Then you have your smart devices that bring to bear the information that you need to act upon the physical world. We're going to focus this talk on the platform. So the platform is from the time that sensor data hits a platform, is captured, the analytics are run, and the insights are derived. And then so that comprises of things like the data and the complex event management needed to capture that data, as well as the operations management that figures out what do you do about these insights and then how do you act upon them. And then finally at the top you have your business applications. But this talk will be really focused on real-time streaming architectures for the platform. So just to really bring this to life, I'm going to start with a demo. And so I promised that we talk through a journey from the initial application that was built through to scaling to different domains and different architectures, different data stores, different use cases. And then how do you handle all of that? So we'll start with the demo that really talks about this journey. So I'm going to talk about a use case that we built for a smart water utility. So this smart water utility has a network with over 100,000 sensors already in place. And so often the first step is to take these sensors in place and then to do analytics on them. And then this water utility, they already had analytics, right? So they were doing your usual batch analytics that took all this data from these sensors and then did things like capacity planning to be able to do things like optimize the distribution of the water network, to be able to identify when sewage backup might impact flow. And these are good for a lot of use cases. But then we're talking about real time here. And so if you have use cases like leakage, you don't want to wait for a batch cycle. So the fastest this batch cycle was able to run was 15 minutes. So that meant from the time that the sensor data hit the platform until when a leakage detection could be figured out was 15 minutes. And that might be too long, and in this case it is too long before remediation steps can happen. And so that's a really perfect use case for real-time streaming data. So we were challenged to bring this time from 15 minutes down to the order of seconds. So let me show you a demo that talks about this. This is the water network. This is the health of that water network, and you see that it's summarized in terms of these data points that show the health. Green being it's healthy, amber meaning that it's not so healthy, and then nothing's red here. But if it's red, that means leakage is currently happening. So amber means that we're predicting that leakage is likely to happen. You should send somebody out and do something ahead of time so that you can prevent a leak before it even occurs. So in this, as I mentioned, it's summarized. So here's a cluster of 24 units. Within that 24 units, I blew it up, so this is the health of those 24 units. Behind each one of these data points is actually that real-time streaming data that I talked about. So let me mouse over it so you can see it ticking. This is that heartbeat view. So it looked really simple in the beginning, right? We had that dashboard that showed the health. But behind every one of those points, we have a number of different sensors. And in this case, there's about 5 of them. You have your flow, your pressure, your critical pressure points, your noise. And it looks perfectly coordinated. So first of all, we're able to bring the order of real-time visibility into your network down from 15 minutes. Now you see this ticking on the order of 2-second ticks. What's happening behind the scenes is that the sensor data is not coming perfectly at 2-second ticks. So what we have to do to make it look like this is actually a lot of real-time analytics. So first off, we need to essentially do data mediation and to synchronize the data that's coming in. So the sensor data is not perfectly synchronized. So first, we have to make it look synchronized for the purposes of doing visualizations, insights, and analytics. Second is that oftentimes in these networks, there's failures. These sensors are not perfectly up all the time. The network is actually very flaky. And so we're also doing analytics that's doing backfilling. So when sensors go down, when the network goes down, we're doing some projections to say that how can we operate as if things are happening so that your analytics and your asset health can still operate even without that data. And then when the sensor is restored and the network is restored, then you're going to need to go back and backfill all that data. So you'll have a burst of data coming in that you'll need to reconcile all the decisions that you made before. So that's just your base level, things that you need to do in real time to accommodate for the sensor variability. Then on top of that, you have all your logic, your domain logic that actually looks at this to detect is something leaking or not. So let me show you that working. So for the purpose of this demo, I'm going to simulate a leak. There's nothing actually leaking in the real water network, so don't be concerned. So I'm going to isolate one of just one of the stations. So all the other stations and all the data is still flowing, but we're going to show one station. And for the purpose of this demo, I'm going to simulate a leak. And so this simulation will show that it turned amber right away. And that was just to show that the prediction is able to, so remember I said we had algorithms that are projecting forward in time. So we've actually detected an anomaly. And then we've detected that that anomaly, if it persists, will show that eventually leakage will occur. And then when it turns red, that's actually when we hit the thresholds that we're saying, if those things that I was monitoring, the combination of noise, critical pressure points, pressure, flow, if it hits that threshold, then the leakage occurred, and it occurred here. And so in reality, you don't do it in the order of what I just did now. It's not operating on the order of 20 seconds, but for the purposes of the demo, we're just trying to illustrate that indeed the math is happening, right? So we have math that is doing both the sensor smoothing of data, the ability to create arbitrary ticks, whether you want something that's at 2-second ticks, 5-second ticks, 10-minute ticks, and then to actually apply this very special domain logic. So this piece of work was really commissioned just to take the existing sensors in play and to very quickly stand up a real-time use case. This sort of thing has to happen very fast. We did this in 6 weeks. And this is needed really to build the momentum and to build the interest that this can be done, right? So that you can gain that internal consensus that this is something viable and that is very useful. So then once this has happened, so we built this, we scaled it up to about 300 different algorithms besides just this one algorithm that I showed you now. And then now I want to talk about the next steps, right? So we have the initial patterns. We can do real-time streaming analytics. Now what? So then there became a lot of interest in the architectures themselves, right? So this is actually implemented. This demo is running on this architecture right here. So once we stood this up and the groups saw the capability, saw that we can do it, then every group has their own hypothesis, how easy it is for me to try this. And so initially you want to be able to clearly automate the same deployment that you did, the architecture, the infrastructure that you need to run it for other groups. So this is just automated provisioning. Well, hopefully it's that simple, but as you know, each group, and in our case, I work for Accenture and we're a consulting organization, so in each client has slightly different requirements in terms of whether their data is currently on-premise, whether it can be in the cloud, whether they prefer Azure, whether they prefer Amazon. So there's actually a lot of choices that takes this initial architecture that we did, and then it wonders, can I do various flavors of it? Right, so if you recognize this architecture, and I'll talk about it later on in my presentation, this is a Lambda architecture. And so this is filled by this Lambda architecture comprising of an ingestion message queue, an analytics engine, we're using Spark, a data store, in this case right now is running on Cassandra, an API layer that essentially sits in front of the data and exposes it to the visualization tier, and then finally the visualization tier. It's running on a certain set of architecture choices. These are architecture specifics. Let me open this again just to show you something. So I'm going to do a demo where I'm going to show not just automated provisioning, but I'm going to show how our automated provisioning is something that actually accommodates a lot of very different types of data stores. So I'm going to live switch out my Cassandra data store to Dynamo data store. And so I'm not suggesting that anybody would do this to a production system, but the story is that if I can do this live, then for sure I can do it static. So that means that with the same pattern, the same Lambda architecture pattern, I can fulfill it using Amazon, using on-premise, using Azure. So this will give you a lot of flexibility in terms of being able to interoperate and go from on-premise to cloud to hybrid, and to really take advantage of the data technology as it comes out. So let's say tomorrow there's some new data store that I don't know of today. Right, so I'm going from Cassandra now, which is a columnar store, which is suitable for time series. And I'm going to move to Dynamo, which is a key value store, which is also suitable for time series. You could also use a relational store. Right, so with a relational store, you probably won't get some of the same performance attributes that Cassandra and Dynamo give you when you're dealing with time series. But from a pure access perspective, this allows you to essentially unlock that data. So now you're decoupling the architecture and the implementation from the actual current instantiation. So here I'm going to come here and I'm going to switch this out. And so DynamoDB, when I switch this out, it's going to be really fast because Dynamo is an as-a-service model, so we don't actually have to turn on VMs in this case. Dynamo, you just need to create the tables, and then once the table is created, then you essentially switch a pointer. So I'm going to switch the table right now. If I go back to my demo, we'll see that there's an error getting the live data. The data stopped. Because the architecture is decoupled, we have the message queue in the front. And because we have the API tier, everything is still up. And then once the tables are created, you see it's live again. Right, so this is not just a resiliency play I'm not talking about here. Right, so the resiliency you get from your asynchronous decoupled architecture using the message queue and the API. This is actually beyond that. This is saying it's more of an interoperability play that prevents vendor lock-in with a particular set of instantiations for your Lambda architecture, but also it means that your data, it's going to point to the fact, and so the end that I'm going to get to is how do you actually take this data that's in different data stores with different technologies and be able to access it all. So this is the demo that I wanted to show to essentially talk about the how. So for the rest of the presentation, I'm going to talk about the how we did all this. Everything from the initial architecture you saw with just the streaming data, all the way through to the automation for managing the different provisioning scripts for the Amazon version, the on-premise version, possibly the Azure, the SAP version. And then I'm going to point to, at the end, this promise and this vision that the data itself within the enterprise data store, the new data stores, the third-party data stores, is now something that you can all tap into and essentially index and be decoupled from both the storage technology and the application use case. So I'm going to start with the initial case. So that initial piece that I showed, just the initial architecture with just the health of the water network, the streaming data, the ability to predict the leak, to be able to smooth out the sensor data. That was something that, again, we wanted it to be very fast, so it took 6 weeks. And because we wanted to be very fast, we chose to use the Amazon Web Services platform. And we instantiated a version of the Lambda architecture. So as you know, the Lambda architecture is a very common architecture for real-time streaming analytics. That's also married with batch analytics. So this is made popular by internet companies like Facebook, like LinkedIn, like Twitter. And the power of Lambda is that you have both a batch leg as well as a streaming leg. And in this case, the batch leg on Amazon, we had Redshift, a relational data store, and we had Amazon EMR, a MapReduce, already in play. And so in this 6-week time period, we added to that use case this streaming leg. So remember, the story is that this smart water utility already had the batch leg. It was operating at 15-minute intervals. So from the time the sensor data hit till the time you can see something was 15 minutes. So we added this streaming leg, and in our streaming leg, we have the stream processor, the message queue in the front. We have Kinesis, that's Amazon's version. Kinesis is essentially taking in data from, we have some streams coming directly from third-party APIs. We have streams coming from an OSI Pi historian, and it's going to hit this platform. Then we chose Spark as our analytics engine, and we chose Spark for 2 reasons. One is because Spark is the sexiest thing about Spark is the algorithms that you write in Spark, so the actual analytics, the same code can be deployed both in a batch mode and in a streaming mode. Spark operates on micro batches, so that means in the streaming mode, it's a very small batch cycle that it captures a lot of the arriving data, and then it runs it. And this means from an operations perspective, you don't need to maintain 2 sets of code. So the code that you test comprehensively over all the data, historical data that you have to train your model, that same algorithm, the best of breed, can be deployed very easily without recoding into the streaming flow. Right, so this is very handy for doing hypothesis testing, and then especially as the network changes, which it will, as those use case changes and the data changes, you can run and batch, brute force over time, learning all the time to say what's the best of breed algorithm, and then just to deploy that into that real-time flow. And then we picked DynamoDB, and again, we just needed something that handled time series data at the rate to write it at the rate that we needed, and Dynamo was a good choice, trying to do something very quickly on Amazon. And then we decoupled this all with this API tier at the bottom. And so the API tier is a really important tier for abstracting and decoupling that application that stayed up, even as I switched out the data store in real time. Right, so that decoupling between the application, that use case, and the data and its interface as it resides is really key. So in this case, the API tier is really doing that. So whether the data comes from Dynamo, it comes from Redshift, it resides in EMR, that shouldn't matter to the application. I just want to get district meter. I want to get all the data within the whole platform. And then, so that same architecture, in that initial 6 weeks, we added, again, this library. Right, so before you can do anything with regards to the domain logic, you have to really take care of the data as it comes in. This is the data normalization process, right? So as the sensor data is coming, again, it's not perfectly synchronized. So we built a library of algorithms to handle the fact that the data is spotty, it's not reliable, it's bursty. When it comes in, it's going to be a big burst. So you want it to appear at any configurable, these regular ticks that you see in blue. So we created an online curve fitting algorithm that was, again, using the same architecture. We trained it offline using this historical data to pick the best shape. And then we deployed one of the shapes with the right code into the streaming architecture. And then streaming-wise, we're at using the most recent data through that real-time stream to do things like adjust the coefficients that we're using. And then we're using that to essentially plot out that blue line. And then using that blue line, we can do two things. We can essentially go back and backfill things. We can go forward and predict things. We can essentially smooth out the time ticks. And then finally, on top of that, now we're ready to add our domain logic. And in this case, we identified 4 typical architectural patterns. So these are just patterns that you need, that based off of these patterns, you can do a lot of domain-specific use cases. So the first patterns is just a computation based off of that streamed inputs. So as the input's coming in, you might want to do something just based off of that most current data. The same computations can be made with the lossy inputs. So now instead of using that most recent data and the real data, you can use that predicted curve instead of the actual data points. The third thing we did was a sort of automated detection. So your usual CEP, complex event processing type based off of thresholding. If you see these events in order and they hit certain thresholds, do something. And then that can use either the real data or it could use the predicted data. And then finally, was a really key one, was around being able to combine that real-time streaming data with historical data. So this is a pattern where, in this example, we're doing a detection of when the reservoir is going to run out of water. Right? So in this detection, we're taking a week's worth of data from the historical data. We're bringing it into Spark, and we're co-locating that with the stream data so that you can do a detection that is, how different is this from that historical data? Right, so with these 4 patterns worked out, now we have the ability to essentially enable all the many other use cases that are taking that same sensor library that we had, and then with these patterns, the domain expert can add a lot more new domain knowledge. So at the end of 6 weeks, we had this, and then it's since scaled. So it's scaled in a couple ways. One is that it's scaled from, so the initial POC, we were running on the order of 100,000 different devices. We had on the order of 3,000 requests per second hitting the platform is what we tested it up to. Seemed okay. I mean, we thought 3,000 was a good start. It was much more than what they needed at the time. Since then, in production, the same architecture is running up to, we doubled that. So in productions, it's up to 6,000 requests per second. The sensor data has, the sensors themselves and the devices have doubled from 100,000 to about 200,000. And then we're in another phase, we're on the cusp of essentially doubling all of that again. So we're going to go to about 400,000 sensors, and again doubling that load again from 3,000 to 6,000, 12,000. Right, so the scale is something that the architecture can handle. But that wasn't too surprising because, you know, internet companies have been running the same architecture for a really long time, and clearly they scale. So the fact that the architecture scales wasn't really the hard part. The hard part was actually trying to accommodate all the different use cases. So as soon as the initial use case happened and we had that Amazon-based stack, then there were a lot of others who were like, oh, we'd like some of this too, except we need ours to be on-premise. A lot of our data store and our data regulations require things to be on-premise. Or they had some use cases, oh, what you did with this smart water domain, couldn't this same thing be applied in the smart grid domain? And then in the smart grid domain, we thought, oh, you could use this for asset health, right, the health of the smart grid network, but you could also use this for intelligent outage and prediction of outages based off of new things like weather, so new data sources. And then at the bottom, you know, like the actual architecture itself, everybody had, like, when you go with the Amazon, we're using Amazon's managed services, Kinesis, Dynamo, Redshift. If you needed to move on-premise, we're actually introducing not just the bottom infrastructure tier, it's not just a new VM, but it's actually the architecture itself. We're changing from the Amazon managed services to an on-premise open source stack like Cassandra, Kafka, If we go to Azure, we're going to IoT Hub. We're going to their own streaming analytics, HD Insight. Right, so as you do this, we wanted to see, so in our case, again, being a consulting company, we needed to accommodate a lot more of these features. So the trade-off here was product versus platform. So I'll talk about it in this way. I view a product as something almost like software as a service, where you can really finally define exactly end-to-end from the stack that you want to support. And that's good because it gives you a lot of control. You're maintaining one stack, and then that gets a lot of efficiencies that you can build and you can really build in. So your infrastructure management and your architecture management, those can be image-based. But as you move to something that's more platform, so the more choices that you want to accommodate down the stack, so the choices at the application layer. If you're just at the application layer, you may be able to just make those choices within the application layer and give an API. If you're now making choices within this architecture layer, then it's not just an API. You have to accommodate these different data stores, these different message queue technologies. So as you move down the stack and you give more choices, that's actually more onus on you. So as you're trying to support agility, the agility to get the 6 weeks, I keep mentioning that because that's a really important number. 6 to 12 weeks is probably about the time that you should be able to turn these around, because otherwise your analytics that you have, you want to be able to quickly capture an initial use case that you can then iterate on, get better data, get better algorithms, get better usages, right? So you need to be able to turn around these use cases fast. And then to do that, you want agility. But as you have more choices in the stack, you can see that agility becomes much harder. And then similarly, interoperability. So again, as I mentioned, you want to iterate. So a priori, you don't know all the data that you need. You don't know all the algorithms that you need. So maybe today, Cassandra and Redshift's all I need. Let's say tomorrow I want to add images. That's probably a blob store. That's a whole new type of technology. Or I wanted to add logs. That's a document store, new type of technology. Right, so interoperability, again, is something very important to think about at this time. So as you allow, though, for more agility, more interoperability, those are essentially conflicting. So we made a choice to support, we had to support both. And so in the demo, this points to one of the things that I showed. We're using a model, and I'll go into the model right after this, but we're using a model that drives the way that you configure the actual system, the way that you index the data, the way that you actually describe the data as it appears, the data that is captured, separately from the way the data is used. The way the data is captured will include things like both your descriptive metadata as well as your structural metadata, right? So your descriptive metadata is around, this is a Honeywell sensor. This Honeywell sensor is attached to a district meter. This district meter is part of this segment of the pipe. It's downstream from these other devices. It's upstream from these. This is all connected to Teresa's house. Descriptive metadata. Structural metadata is actually about what does the actual data look like. This is time series. It's a double. How do I interpret that? Using this metadata model, we're going to do a couple things. We're going to be able to figure out the data stores that it's going to go in. We're going to manage the interfaces to those data stores. And then we take the same approach and we use this to also manage the analytics that accesses the data, as well as the applications that use it. So in the example that I was showing, let's just start with just the infrastructure. Right, so I talked about just the infrastructure model first. So in the infrastructure model, because we're trying to support all these different types, not just one stack with Amazon, but also on-premise, open source, Azure, SAP, something I don't know about coming down the line. Because we're architecting for that use case, we started with a model that's based off of the Tosca standard. So this Tosca model is an OASIS standard that OpenStack is based off of. And we purposely represented it as a graph. And so this will be the theme for the rest of my talk. a lot of these use cases, the way things are connected both in the world, right, the way that the relationships of the devices, as well as the relationships of where the systems themselves, the architecture, the analytics, the apps are using it, these are all graphs. So we represented this as a graph structure, and we do this because it's extensible. So when I want to extend to an Amazon specific, so here's an infrastructure as a service VM type model, that node, an expert in the Amazon domain, can update this model with what it means to be an EC2 instance. An EC2 instance is a type of VM. It has certain properties, whether you're small, a medium, and large, whether you're memory intensive, whether you're storage intensive, right? So as you do this, you can have an expert onboard these models that describe the knowledge as to what does this thing do. And then we use this knowledge as to what does this thing do, and we couple it with a pointer to the actual chef scripts. So in this case of infrastructure automation, we're pointing a description of the thing that you want to procure, an EC2 instance, with the scripts that actually execute on this. And using this, we were able to essentially orchestrate and manage the deployment of a lot of different types. So as I onboard the VMware version within my data center, your data center, different experts would onboard a description of what that VM is, and there will be different scripts as to how, maybe they're all chef scripts, but there will be different mechanisms, different credentials, different endpoints, different things that you have to apply to access it. And so using this particular model, it captures both the knowledge as well as the interface, and we're able to play it back and do the automation. So using the same approach, we're able to do things like manage our analytics models, so the different analytics that actually need to, again, be deployed into Spark to be able to figure out which data you need to pull in, the interfaces to that data, and then to the visualization elements. And so in this journey, it didn't start off with us thinking graph for everything, but it turned out that we were managing a lot of our deployments because the way things are related was a graph. And so that brings me to our lessons learned. So we started implementing and we were managing this platform using graphs, and then we stepped back. And we realized metadata really unlocks the data in the platform and the data in your partners and the data in third-party environments that you need to essentially bring together the context that you need for new use cases. So metadata, that's, as I mentioned, is the data about the data. But in this case, let's talk about, again, bringing it back to the sensor world. You have your historical readings, your sensor network readings, your usage readings. Those are from sensor data. That by itself isn't going to get you that far. To actually hit a lot of these use cases that you want, you need to actually bring together things like maintenance logs, bring together things like service orders, things like your customer contacts, your customer service records, your site manager contacts, your site inventory. You need to bring this together, and then what you bring together depends on the use case. In some cases, it's noise, and in some cases, it's useful. How do you know what to bring together? The metadata is going to tell you, right? So if I care just about sensor readings, then I'm going to be able to say, I care about a network segment. And when I care about a network segment, I'm going to need the site inventory to be able to essentially join that against your sensor readings to know what makes sense. If I care just about, all things that are Honeywell sensors for a particular type, I want to look at the supplier inventory and the supplier logs with the actual sensor readings. Right, so what I bring together at any one time, it really depends on what I'm trying to solve. And I don't know that all ahead of time. Right, so to manage this, you need to actually capture the data in relation to what is it actually measuring in the world. So this data is typically not all contained within one storage device. And if you brought it to Hadoop, your data lake, it would no longer be real time. Because once you bring it to Hadoop, you're essentially doing an ETL process, and by that time you have a copy of the data, and you're already out of date. So you'll always be acting on stale data, a different view of actual reality. So what you want to do is to keep the data in its single source of truth. And so here we map the data to The data stores, marketing thought my data stores look better as squares instead of cylinders, but they should be cylinders in the back. Right, so you have certain types of data that belong on different types of data stores. So let's assume that's the single source of truth. This is what you want to index over. And so in our model, since we were using the models to do things like be able to manage our infrastructure, how it's related to the analytics, how it's related to the application use cases, here's how we're indexing the data. So within, we have two sides. Remember I talked about descriptive metadata as well as structural metadata. Our domain knowledge graph describes an asset hierarchy. That's what we show in the illustration. The asset hierarchy is something that as you switch domains, you get a new domain expert or a new expert to essentially update that asset hierarchy or that domain knowledge. If you don't like this, so let's say I go to your water network and it's slightly different. You have another thing on there, critical pressure points. That's a really important thing for you. You extend the graph, you essentially draw an arc on it. Or if there's something that's there that on this model that you don't have, you erase that arc. Right? So this becomes a very object-oriented, abstract model that you can inherit from, and you can choose to override it or choose to accept it as is. But that's a domain expert captures that knowledge. Separately, a Cassandra expert or Dynamo experts captures how do you actually access the data. And using this, we're able to, our vision is we're able to now manage your enterprise data store, the data as it resides over all these different types of technology, in a way so that you can route the data to the appropriate data store as it goes in. So this is on the ingestion pipeline, you're managing the ETL, right? So the transforms that need to be applied, the place that you're going to route this to. On the consumption layer on the top, the things that you need to essentially figure out which data stores you need to get something from to configure either your API or your data virtualization pipeline. And then to actually explore the data. And as we look to exploring the data, again, to take a note from what internet companies are doing all along, what you have now is your data indexed with the knowledge graph. And so if you search for things on Google, search for things on Wikipedia, you'll know it's not just the content, it's not just the results. They have assembled a card. There's a card that if I search for Tom Brady, I know Tom Brady is a person. So Tom Brady has a spouse, Tom Brady has a birthday, Tom Brady has an occupation. Because I know Tom Brady is also a football player, it has a Super Bowl records, it has the things that he's won. It would be different if I searched for our CEO, Pierre Nanterme. It knows he's a person, but he's a CEO. Right, so using this, we're now able to better assemble the data in your enterprise data stores in a way that is easier for your analysts, your data scientists to discover. And this, I think, is key. So if we talk about real-time streaming architectures, and we want to enable this ability to quickly think of new use cases, we talked about interoperability to be able to manage the actual deployment and complexity. But just as important is this piece that I'm talking about now, to essentially enable your data scientists and your business analysts a more friendly way to find the data. So here in this example, we show that they're looking for something called a district meter area. That's something that we had in our water network based off of the asset hierarchy. Because I know a district meter area is a place, we have a map. And these are the assets that are available in our data stores, and the data resides on Amazon. I think it's a Dynamo and S3 here. So I think this is the vision that we had. So reality today, you have this architecture. And then I pointed to some ways that we manage our infrastructure using these graph models. And then I point to vision as to things that we're thinking about and we're doing right now in a prototype mode to be able to make it more easy for the data to be discovered, to be used, and to quickly adapt. Thank you.